welcome back. I hope everybody's had a good first week. We're talking about the sup and the inf. By the way, we probably will have homework due tomorrow. I need to look and make sure we did enough. Not tomorrow, next week, on Wednesday. Sorry. Yeah. I think we've done enough stuff to make our first assignment. So I will post it at our website sometime today. I'll send you an email this time just to remind you that it's all there. It's due on Wednesday on Gradescope. I hope you have all used Gradescope before. Please let me know if you're having trouble doing it. It's easy to do. And they have an app now. I don't know if the app is any good. Have any of you used the app? They have an app. Or you can just use it through your web browser. All right, we are still talking about the axiom of completeness. Which I'm going to write sometimes as AOC. The axiom of completeness is a fundamental property of the real numbers. Some like very intuitive version of the completeness is just that there are no holes in the real line, but the formal way that we've said it actually sounds quite different. It's just that any bounded set has a sup. It turns out it also has an inf. If you require that every bounded set has a sup, I should say, sorry, bounded. Every set bounded above. Can I insert the word above in there? And remember, the sup means the least upper bound. It is a fact in the real numbers that if your set has some upper bound, automatically it has a least upper bound. All right? That's called the axiom of completeness. It's called an axiom because we're not going to try to prove this. This is a property. You could think of this as part of the definition of the real numbers. Although we're not really going to get into what exactly is the definition of the real numbers. That I don't want to talk about that. All right. Every bounded set, every set which is bounded above has a sup. Okay. And remember, last time we talked about the sup and the inf and did several examples. For instance, what is the sup of, let's say, this set? This is one of our favorite sets for this course. Set of all 1 over n, where n is a natural number. And what about the inf of that? Same thing. This set, if you were to kind of draw it out, it goes up to 1 here, and then also 1/2. And then 1/3, and so on. All of these fractions. I suppose it never quite gets to 0. So what's the sup of that set? Sorry, I'm off the bottom. 1, yeah. It's the least upper bound. All the upper bounds would be over here, things greater than 1. 1 is also an upper bound, and it's the least of the upper bound. So the sup is 1, and the inf? 0, yeah. The inf would be the greatest of the lower bounds. All the lower bounds are over here. The greatest of the lower bounds is right at 0. Yes?
So it doesn't matter, like, what direction it goes? Like I was thinking yesterday, like, as you increase n, it gets closer to 0. It's like, if you make it bigger, it gets to 0. So it's like...
Yes. It is a little weird, I guess. Yeah, it's because of the way denominators work, I guess. When you make the denominator big, yeah. Yep. All right. This example here shows you that the sup sometimes is part of the set originally, and the sup sometimes is not. So here the sup is 1. 1 is actually part of the set, whereas the inf is 0, but 0 is not a member of that set. So sometimes it is, sometimes it isn't. All right. Any questions about that? This is the sup and the inf. All that from last time. I would like to talk about one more theorem about the sup and the inf, and then we'll talk about something a little different. I said several times, and some sort of intuitive way, the sup is like the closest point you can get to the set on the right side. it's like right there. It's up here is too big because there are other lesser upper bounds. The soup is the smallest of all the upper bounds, which is to say, you could say something, I'll put this in quotes because it's not very technical, but like the soup is something like the nearest point to the set on the right side. And then the inf would be similar, but on the left side, right? Inf is same thing on the left side. I want to try to turn this informal statement into some real language and then try to prove it. So how can we make this? I'll just say it about the soup, but you could say any of these things about the inf. I want to formalize that. It's a bit of a journey to formalize that. The nearest point, when you start talking about near points, points being near to one another, the way to formalize that is in terms of those epsilons. And that's why I want to do this as an example again, because this epsilon point of view is really super important for the whole semester. The way that I think about this thing on the right side about the soup is kind of like if you have the soup is a point which is so close on the right side that if you were to move that point to the left any amount, any bitty little bit, it would no longer be an upper bound of the set. Like one of the points from the set would go to the left of one of the points in the set. So this is not quite formalized. This is not my formal version, but it's something like if we move the soup even a bit to the left, well then we will have moved it past one of the points in the set. That's the idea. That's because the soup is supposed to be the closest you can get on the right side, but still on the right side. And if you move that point any more to the left, it will pass over one of the points in the set. So if we move the soup even a bit to the left, then it goes to the left of some point in the set. And this is not so hard to say using epsilon. And the epsilon is what I'm going to call this bit. I'm going to say for all epsilon greater than 0. That represents the little bit. And just like the example with the epsilon thing before, if you say this correctly, you don't actually have to say that epsilon is really small. It's just sort of built into the whole formula. So here's what it looks like. I'm going to write this as a theorem. It looks like let S be an upper bound of some set, I'll call it A. Then S is the soup of A if and only if, I'll write this double arrow here. And now I'm going to say some epsilon business. For all epsilon greater than 0, you think of this epsilon as representing a little bitty distance. And now I want to say something like this. If we move the soup even a little bit to the left, then it goes to the left of some point in the set. Here's how to say that. When I say move the soup a bit to the left, well, I'll write it and then we'll try and decipher it. There exists A in A with S minus epsilon less than A. That formal stuff means the same thing as what I was trying to say before. If we move the soup even a bit to the left, where you see that is right here, S minus epsilon. That represents S, which is the soup, and I move it to the left a little bit. That's why it says S minus epsilon. And if you do that, it goes to the left of some point in your set. So that's why I said there is some point in the set, so that S minus epsilon is now to the left of that point on the number line, right? S minus epsilon is less than A. So this is a little, if you're not used to writing things this way, which I assume you are not, It's a little convoluted sounding maybe, but this is exactly the way that we make this kind of idea formalized. Yeah.
Is the double arrow the same as if?
Yeah, this means if and only if. If, just if with one F would be like one direction of the arrow, but not the other way. Yeah. All right. This is a very useful characterization of the soup. The soup, if your number is the soup, it means that this is true. This, I don't know if this seems useful. Actually, we're going to use this version of the soup later on today, maybe, if we get that far, or if not, next time. All right? I want to see if we can do the proof of this, and then we'll move on to something a little less technical. So let's see if we can do this. I'll do this way first. I don't know if either way is easier in this case. So I am going to assume that S is the soup of A. That is, it is the least upper bound. And I want to prove that stuff over there. Perhaps you remember, when I need to prove something which begins with for all epsilon greater than 0, I begin the proof by saying, let epsilon greater than 0 be given. Then I have to show that stuff. So assume S is the soup. Let epsilon greater than 0 be given. And I want to show this. There exists A with S minus epsilon less than A. Now I could say I want to show there exists, but I usually say something like, we will find A such that S minus epsilon less than A, right? This is what we got to do. We have to find some point so that S minus epsilon is less than that point from the set. Okay? Unfortunately, there's not a lot from what we're saying here that will allow you to just finish the proof. You have to think about this a little bit. What we have here is I want to say something about S minus epsilon. S is the least upper bound, and then I subtract a little bit from it. What does that mean about when you subtract a little bit from the least upper bound? If S was the least upper bound, that's what the soup means, right? S is the least upper bound. So that means S minus epsilon is not an upper bound. That's because it's a little bit less, right? S is the least of the upper bounds. If you make it a little smaller, then it can't be an upper bound anymore, because S is the least of all the upper bounds. So if you subtract the epsilon from S, it becomes some other number which cannot be an upper bound anymore. All right? S minus epsilon is not an upper bound. Can anybody say, what does it mean that it's not an upper bound? Yeah?
There's some element in A that's greater than it?
Right. To say it is an upper bound means it's bigger than everything in the set. If I say it's not an upper bound, that means there is something in the set which is bigger than that. All right, so this is not an upper bound. So whoop, there is an element of A with S minus epsilon less than A. And wouldn't you know it, that actually, this is exactly what we wanted to prove, right? That was the whole point of this direction of the proof, was to show that there exists A in A with S minus epsilon. I wrote exactly, that's exactly what we needed to show, all right? So I will just say, put a little shoe right there, right? It's because when you start with the least upper bound, if you subtract a little bit, it's not going to be an upper bound anymore. Which means, it means this. It means there's some point in the set which is bigger than S minus epsilon. All right. Half of the proof. Any questions about that? We are just kind of playing around with definitions. There's not really such a big idea here, although, like I said, if you're not used to doing this kind of thing, this can seem very confusing the first few times, and maybe all the remaining times also. It is a little confusing, so that's all right. Okay, let's try the other way. So we assume this business here, and we have to show that S is the sup. And notice that I also assume overall that S is an upper bound. All right, so we don't have to prove that it's an upper bound. We just have to prove that it is the least upper bound. So this direction, I assume there's really not much more to say other than just to write it out. We assume for all epsilon greater than 0 there exists A in my set A with S minus epsilon less than A. All right, and what I want to prove, we must prove that S is the sup of A, but we already assumed that it's an upper bound. So all we got to do is show that it is the least of the upper bounds. It is already assumed to be an upper bound. We assume it's an upper bound. So we need only show it's the least upper bound. All right. This is a little tricky. Maybe this part of the proof is a little trickier than the other part. To show something is the least, this is something that you just see with experience. Showing something is the least upper bound is usually a good idea to do this by contradiction. So I'm going to assume that it's not the least upper bound. That means there's another upper bound which is lesser, and then see if we can make a contradiction for that. So I'm going to say, for the sake of a contradiction, let's assume there is a lesser upper bound, smaller than S. So let's say T less than S. T is an upper bound. All right. And what we know is this. This is a little weird looking, so maybe hard to know how to use that. But it's meant to be. We can use whatever we want for that epsilon. You think of epsilon as being a really small distance. No matter what the epsilon is, you know this has to be true. So maybe I'll try and draw. I don't know if this is going to be helpful, but let's say like this is my set A. And we have S, which is some upper bound, which we're trying to show is the sup. So maybe I'll draw it a little closer, right? And then we are assuming also that there's some other upper bound T, which is lesser than S. So maybe some other point, say here, T, right? Two different numbers which are like competing for the title of least upper bound, okay? The reason I draw the picture is because I want to somehow use some particular distance as the epsilon in here, right? We know that this statement is true no matter how small this number epsilon is. And I was trying to draw the picture to make me think of some kind of very small distance that I could try to use for the epsilon up here. Anybody got an idea? Yeah.
T minus S.
Yeah, I think he said S minus T, right? You need it to be positive. If you S minus T is the distance there because S is greater than T. Yeah, how about this? No, this little distance here. I'm going to say let epsilon be T minus S. And hopefully that will do some good stuff when I plug that in up here. All right? What we're trying to do, remember, is to derive a contradiction. Okay, so let epsilon equal T minus S. Then, what does that mean? I scrolled away, but what we assumed at the top there is for any epsilon, in particular T minus S will work. There exists a, you say T minus S? It should be S minus T. What am I thinking? I corrected you before, but he was totally right. I don't know what I was thinking. Sorry. S minus T. S minus T. It has to be positive. T minus S is negative. Okay. Then, anyway, I'm going to write what we see up here. No matter what the epsilon is, so I'm using s minus t, there exists a, so I'm just going to write that. There exists a in a, such that s minus epsilon less than a. S minus epsilon means s minus t. Like that. Alright? I plugged in s minus t for epsilon. Can we derive a contradiction from this? I hope so. We can simplify first of all, right? This is like the best part of the day. Best part so far. If you weren't understanding anything, at least you will understand this. Distribute the minus sign, right? So that must be true. Cancel the s's. That's about as simplified as that's going to get. Remember, I'm looking for a contradiction. Is that a contradiction with anything that we said before? Yeah?
Yes, because we said that t was less than s.
Yeah. That's true.
That means s has to be the least upper bound.
Yeah, I think that's right. I think there's a maybe clearer way to say it. Yeah, right. We said already t is an upper bound for the set, and here I just said t is less than a, where a is some element of the set. So there's a lot of ways you could make the conclusion here, but I will say, so t is less than a, so that means t is not an upper bound of a, and that is a contradiction with this up here, right? T is an upper bound, t is not an upper bound. That little symbol sometimes is what I write when that means there's a contradiction. This is like two things canceling each other out or something. Alright? That's the end of that. All of this was, remember the idea was trying to formalize and then prove this fact that the soup is like the closest point on the right. And the inf, we didn't do the inf, but it's the same thing, just change all the inequalities. The inf is the closest point on the left side of the set. Alright? Any thoughts about that? Alright, let's talk about something a little more intuitive, maybe. A little less proofy. So this was actually that's the end of the first section in our textbook that we were covering, which is called the axiom of completeness. The next section in the book is called consequences of completeness. So this is like some fun facts, consequences of completeness. Fun facts about the real numbers that you can prove using the completeness axiom. These are consequences of completeness. So here is our first, we're going to talk about like two major consequences of the completeness axiom. And the first is, I'll just write it as a theorem here. It's called the nested intervals property. In our book, abbreviated the NIP. I'm not making that up. The nested intervals property. All right. This is about nested intervals of real numbers. I'll write it as a theorem, but then I'll draw a bunch of pictures and we'll talk about a bunch of examples. So it involves a bunch of different intervals. Infinitely many different intervals. You take, I1, I2, I3, they're all different closed intervals. And I'm writing them as closed intervals with two endpoints, right? The left endpoint is an, the right endpoint is bn. So you have the first interval is a1 to b1, the next interval is a2 to b2. And we assume that they are nested. That is to say, in is a subset of in plus 1. for all n. That is, each one is a subset of, sorry, I meant the other way around. Each one is a subset of the previous one. That means it's like this. The next one is always a subset of the previous one. All right. So a picture, maybe I'm about to write the conclusion of the theorem. I'm going to leave a little space, but I will draw sort of the picture you should have in mind is, here's my whole real line, and I begin with one sort of biggest interval, I1, and then there's a subset of that, which is I2, and then there's another smaller one, which is I3. Maybe some of these could have the same endpoints. That's allowed. They have to be subsets as you go down, right? Each next one is smaller than the previous ones and living inside of the previous ones. And the conclusion of the theorem has to do with when you take the intersection of all of these intervals. That is, I ask what points exist in all of them, not just the first few, but which points exist in all of them. And the nested interval property says, then the intersection of all the intervals, which you would write something like the intersection I equals 1 to infinity, I'll use a little n, sorry. N equals 1 to infinity of In. That's a big intersection. It means I'm just talking about the points which are in all of them. And the conclusion is, it is not the empty set. That's all I'm saying. Actually, you don't know much very specifically about this, but it is true. If you have nested closed intervals, their intersection is not empty. That's the conclusion of the nested intervals property. So it means basically, if you do this, but you have infinitely many of them, they get smaller and smaller every time. They cannot shrink all the way down to nothing. There has to be at least one point which is in all of them. All right. This never becomes the empty set. If you take an intersection of infinitely many nested closed intervals, it never becomes the empty set. That's what the nested intervals property says. And the way you prove this is using the completeness axiom, although I don't want to do the proof just yet. Let's just look at a bunch of examples. So here is a standard example. What if In is the interval minus 1 over n to 3? So this is an example in which all these intervals have the same endpoint on the right, which is 3, but the endpoint on the left is moving, all right, from one to the next. So you could say, I1 is negative 1 to 3, right? I2 is negative a half to 3, etc. Negative a third to 3, negative a fourth to 3. If you want to draw a picture, it'd be like, here's 3, here's minus 1. The first one goes all the way across. The next one, that's 0, say. The next one only goes to minus a half. The next one goes to minus a third, then minus a fourth, etc. Right? Now, it is important that they all be closed intervals, which they are. And it's also important that they all be nested, which they are. You can tell each one is contained in the previous one. In fact, each one is contained in all the previous ones, because that's how nesting works. All right? In this case, what is the intersection of all them? Anybody want to say? What do you end up with? The intersection would be the set of all points which are in all of the intervals. Yeah?
0 to 3.
The interval from 0 to 3, yeah. Is it including 0 or not? You have to think about, is the number 0 actually going to be in all of these? I think actually it is. Yeah, this is a little strange. You have to think carefully about it. But yeah, I think it's true. This number 0 is in all of them. These left endpoints are going to approach 0, but they won't actually move through 0. So, and the 3, is the 3 included in all of them? Yes, that's a little less interesting, but yeah. All right, so in this case, you get a closed interval from 0 to 3, and that's not the empty set. Right? All that the nested interval property doesn't necessarily say you end up with an interval. It just says you end up with something which is not the empty set. All right. One way, from a certain point of view, if you want to make this sound obvious, one way to think of this is by saying, when I look at nested closed intervals, one point of view you could take is that I start with a big interval and then I keep on like zooming in on parts of it by zooming in on increasingly smaller intervals. Like up here, I started with this whole picture, and I keep on zooming in on parts of that interval. All this says is if you continue zooming in forever, you can just keep on zooming in forever. You're not going to like run out of stuff. You're not going to end up with nothing if you zoom in far enough, right? Which, from a certain point of view, that is obviously true of the real line. You can zoom in as much as you want, and it doesn't like go away. If you ask me why exactly is that true of the real line, at some level my answer would be because there's no gap in the real line. Like if there were a gap, you could zoom in on the gap, and then eventually you zoom in so far enough that you have nothing left. But that's not possible in the real line because there is no gap. That's why I'm trying to give you an intuitive notion of why this has a lot to do with the completeness property, which is about there are no holes in the real line, right? Rather than talk about that technicality at the moment, I thought I wanted you guys to maybe play around with this. Oh, here's another example. How about the intervals are, let's say, 2 minus 1 over n to 5 plus 1 over n. You should convince yourself, first of all, that they really are nested closed intervals. I mean, you can tell they're closed intervals just because I said so. The brackets are closed. Are they really nested, though? 2 minus 1 over n. So that means that I1 is 2 minus 1 to 5 plus 1. This is 1 to 6, right? And then the next one, I2, would be 2 minus a half to 5 plus a half. That's 1.5 to 5.5, which really is like that, right? As those fraction parts decrease, the left-hand endpoint will be moving to the right a little bit, and the right-hand endpoint moves to the left. I think these really will be nested. And in that case, can we say what's the intersection? What do you think? Yeah. 2 to 5, yeah. And you think it should be the closed interval still? Yeah. I think so. For the same reason as before, you can kind of imagine looking at this formula and say, like, what happens when n goes to infinity? Something like that. Those fractions would just disappear, and you get from 2 to 5. Is there a question about that? No? All right. I got some for you to sort of explore with. So I would like to think about this nested intervals property. So remember, it says nested closed intervals have non-empty intersection. That's what the NIP says. Take a few moments and think about this. You can chat with your friends if you got any. Can you make an example? I just want you to play around and get a feel for how this thing works. Can you make examples where? How about nested closed intervals? In all those examples we've done, the intersection has been another closed interval, but is that necessarily true? So see if you can make an example where nested closed intervals have intersection of 1 point. One single point, exactly 1 point, not a whole interval. But you shrink it down and it makes just a single point. How about nested closed intervals have intersection of an open interval. In all the examples we did, you get a closed interval at the end. Can you think of a way to do it so that you get an open interval at the end? I got two others to think about. All right, the nested interval property says if they're nested and closed, the intersection is not empty. Can you find an example where they're nested but not closed interval, and it turns out the intersection is actually empty? And then also that they're an example where they're closed but not nested, and the intersection is empty. Take a few minutes, see if you can think of these. I will tell you, one of these is impossible. The other three are possible. So if you feel like one is hard to do, it may be because that's the impossible one, but I'm not telling which one. I'll tell you later. See what you think. The first one is not impossible. Yep. The first one.
I think you said the same thing about that. Yeah.
Where it moves the Like I know it's funny, but I don't know the same thing.
Oh, like the open. It's not
Yeah, we were wondering if we
What's
had
next?
Yeah, we can.
Same thing, 3 is
They're kind of on this. That's not, that doesn't count as a close.
That's still inside. That's why we started this.
It's 1 point. And it's not necessary.
It's the same thing.
It's not necessary. The only change is, it's like 1 to 1, that's all the change. Oh, the 90 off. Actually, one mark with a not necessary.
Probably a plus. supposed to go the other direction, one of the other directions. Like it's supposed to increase.
Okay.
Oh, that's.
Yeah.
No, the left side. The left side.
No, really, and then that goes to infinity.
Left increases on the right side.
Yeah, no,
Yeah,
that's
oh, that makes sense. Constitute.
Sorry,
No, I'm
like,
Closed interval?
over n.
Whenever you write first, it's the bottom,
Yeah.
the lesser one.
Oh, so it's kind of backwards,
So
okay.
you just wrote the number.
Yeah.
I guess,
But it's not.
Because this is
the max number first. Zero to
Oh,
one.
wait, 'cause if you're adding a fraction.
Right, so it'll keep getting smaller, but all of the ends are not needed, so.
Like if you're two, you might start subtracting smaller and smaller.
Yeah.
Or if you're adding a right. Right, the bigger one, trying to get.
Nested but not closed. Yeah, I would suggest maybe just think about the other examples, but what happens?
Right. Because they're not nested.
No idea.
Let's talk about it in 2 more minutes.
let's It just has to approach a number, it can't be that number. That's the thing, it's maybe like, it's not like.
How can we make it one of those? Not be a number.
It's like what the solution is.
But then again, I have to teach
Like basically like we asked them to provide an answer. That's like what the answer is. How about like that? Without that, like.
I think you could do it on weird.
That is not an
Probably the square root or something. What is it about it? What is it add on those? Always zero.
Always zero.
All right, let's talk about them. I've heard some very enthusiastic and vibrant discussions. It's great. As I was going around, I thought a lot of people figured out the first one. Nested closed intervals, which have an intersection of a single point. I think to me, the simplest way to do that is like this. There were some variations of that, but this is what most people ended up with, something like that. Negative 1 over n, so it starts off like minus 1 to 1, this is the first one, and then minus a half to plus a half, and then minus a third to plus a third. These shrink down, eventually shrinking all the way down. The only number which is in all of them is 0, right? So the intersection here, n equal 1 to infinity, is, the way, if you want to write this technically correctly, it would be that, right? It is the set containing only 0. Any questions about that? I saw a lot of people came up with something like this. That's great. Some people, for some reason, did like 2 minus 1 over n and then 2 plus 1 over n, which is a slightly more convoluted version of this. All right? Great. How about the second one? Nested closed intervals, but their intersection ends up being an open interval. Did anybody figure this out? I saw some attempts. All were wrong. Actually, this is the impossible one. This one you cannot do. So there is a theorem which we will talk about much later in the class, that the intersection of any number of closed sets must be a closed set Now we'll have to talk about what exactly closed set means. It doesn't have to be an interval. It turns out a single point is a closed set, and so this kind of thing is possible, but an open interval is not a closed set, and so that is not possible. So this is impossible. Maybe I'll just put a big old red line through that. How about this? Nested intervals, but they are not closed intervals, and they end up having an empty intersection. I gave a hint to somebody, like, you could just play around with some of the other examples we've talked about, but see what happens if you make them open intervals rather than closed intervals. Can you get anywhere with that? Anybody come up with an example for this? Yeah? Okay, this is a good idea, which I think does not quite work, but if I did something like open interval minus 1 over n to 1 over n, open instead of a closed interval though. So the picture of it will still look like it goes minus 1 to 1, and then minus a half to a half, minus a third to a third, minus a fourth to a fourth. I would say the intersection of this, the big question is, does the intersection still contain 0, or is it just contain nothing? I think actually the intersection still does contain 0. The number 0 is in every interval like this, right? So this is not quite an example. You can change this though. Does this give anybody an idea of a modification? If you actually consider only half of this picture, I mean one side of it, that will suffice as an example. Does that give anyone an idea? Yeah. Yeah, if I just do 0 to 1 over n as an open interval, so this right here doesn't quite work, but 0 to 1 over n. So this one goes 0 to 1, and then 0 to a half, and then 0 to a third, 0 to a fourth. This time, because you are, the right endpoint really is going, in the limit here, going to tend all the way to 0. There will be no numbers left over in the middle, right? The middle kind of shrinks every time. So here, this one, if that's my in, then the intersection of in really is the empty set. All right. So the nested intervals property is a property of closed intervals, not open intervals. I mean, sometimes it works for open intervals, but in general, it doesn't. Yeah.
So why does it end up being nothing versus just ending up on
with 0? Yeah. Why isn't 0 just the number 0 in all of these? The answer is no. Actually, 0 is not in any of them because it's excluded, because this is an open interval, right? It's a technicality, but none of them has 0 in it. And so 0 is not part of the intersection. You might be tempted to write, I saw some people writing things like, isn't the intersection like the open interval from 0 to 0? First of all, that's not really an open interval. You're not supposed to write the same number both times, even in a closed interval. But that, even if that does mean something, it means the empty set, right? It's all the numbers between 0 and 0, but not including 0. There's no such numbers, right? So this really is the empty set. We wouldn't typically write it as 0, 0. How about this one? Closed but not nested, and the intersection ends up being empty. I think I saw somebody get something like this. Not nested intervals. Anybody want? Yeah, the closed interval from n to n plus 1. Actually, if you think of intervals which are not nested, they usually will have empty intersections. So what this is, if I were to draw a picture, it would go, this is like the interval from 1 to 2 is the first one, and then the next one is the interval from 2 to 3, and then the interval from 3 to 4, and then from 4 to 5. That's what these intervals look like. And then what's the intersection of all of these? What are the numbers which are in all of them? The answer is there are no numbers which are in all of them, right? Not even in most of them. Because they are not, like, if they're not nested, then the intersection is definitely going to be empty. That's what not nested kind of means. Okay, so here, the intersection of n to n plus 1 is the empty set, all right? So the nesting is important. All of this is meant to explain that closed is important and nested is important. If they're not closed or if they're not nested, then that property is not satisfied.